Hello everyone. This is a 48 volt to 400 volt boost module that has been running continuously for over a year. Its only real drawback is the efficiency. At full load, the conversion efficiency is pretty poor, barely under 90%. So I decided to design a brand new converter to replace that aging one. The new module reaches up to 96% efficiency at maximum load. It runs cool and quiet, and I've added multiple protection layers to make it even more robust. As you can see, I'm currently testing it at over 3 kilowatts of AC output power, with an input current of around 70 amps, and the module is still operating very stably. The fan is only at about 10%, and the temperature stays below 40 degrees Celsius. Thank you to JLCPCB for generously sponsoring the PCBs for me. I used to make PCBs by hand, and I could only manage small single-layer boards. That really limited the creativity of my projects. Everything had to be simple enough to fabricate at home. But now with JLCPCB, that limitation is gone. I can freely design 2-layer or even 4-layer boards at a very low cost, and the quality is absolutely perfect. Also, don't forget that JLCPCB is running their biggest sale of the year for Black Friday. You can grab tons of discount codes for your projects right on their homepage. Just check the link in the video description below to claim these offers. After more than a week of waiting, I finally received my PCBs. And just like every time, the quality is absolutely flawless. This boost converter uses a full bridge topology. I'm using 10 ohm gate resistors along with a fast diode in parallel to quickly discharge the gate during turnoff. This design helps the MOSFETs switch off faster and prevents cross-conduction. We'll need 3 separate aluminum heat sinks. The MOSFETs will be mounted directly onto the aluminum without any insulating pads. I usually install the heat sinks first before mounting the MOSFETs. Doing the MOSFETs afterward makes it much easier to line up the screw holes. This design uses 24 140A MOSFETs. Based on the calculations, it can handle around 6 kilowatts at 48 volts without any issues. And if you run it at a higher voltage, the achievable power will be much higher. I'm using 2 470 mA 450 volt capacitors on the output. Obviously, at 6 kilowatt that's not enough. You'll need additional external filter capacitors, at least 2 more 470 mA caps. Also pay attention to cooling the filter caps. In my design, the capacitors are placed in the middle. Airflow from the cooling fan passes over them and cools them quickly. This is the main transformer. I'm using 3 amorphous cores, each 50 millimeters in diameter. These 3 cores can easily handle 6 kilowatts of power. This is the circuit, almost complete. Only the primary winding is missing. Once that's in place, it'll be fully finished. Here's another version. This one uses 2 63mm cores and can also easily deliver 6 kilowatts of power. I'm using Litz wire with a total cross-section of 20mm squatters for the primary winding. I installed one to pair with my grid tie inverter, and it works perfectly. Of course, you could also combine it with an H-bridge circuit to create a proper sine wave inverter. It works flawlessly in that setup as well.